Okay, well, I goofed and I just recorded writing all this down and drawing these beautiful pictures out, and then my audio was not recording. So I'm going to go through this again just using the same picture. So talking about states of matter, we're talking about states of matter. That means the state at which the matter is in. So by state, we're talking about solids, liquids, gases, or even get into plasmas, but we're going to stick with these main three. So plasmas are you can kind of describe them as like a charged gas, but we're going to stick with these three. So solids have these little particles, and if you'll notice, each of the little blue dots that I drew in these little areas, there's 16. There should be 16 if I counted right. There's 16 dots in each one, and so with a solid, this is a low energy state of matter. And what I mean by that is that the molecules are vibrating back and forth. So if you could zoom in on that little cylinder, these dots, I'm just going to do one row of them. These dots are vibrating side to side, up and down. They're vibrating barely. I mean, they're just barely moving. Any object that you've ever touched or been in contact with is not moving. I mean, is moving. There's no object that you've seen, unless you've touched something that's 0 degrees Kelvin, you've not touched anything that is completely still. So the desk that you're sitting at, the phone that you're holding, the pencil that you write with, everything is moving. So they're vibrating, moving very, very slowly maybe, but they are moving. And so solids have the least amount of energy because they are vibrating the least, the least amount. The liquid, if you move into a liquid, as you move into a liquid, they have more energy. Liquids have more energy than solids, and gases have more energy than liquids. And what I mean by that is these molecules are moving faster. With liquids, I use a little phrase that you'll probably see again. They are sliding past one another. They slide past one another. And gas molecules are the most energetic of the states of matter, and we'll even put that above plasma. But gas molecules are even more energetic, and they are zooming past each other, which means they have high energy, but because of the distance between these molecules, that also means that they can get smushed and get compressed more easily because there's a lot more room in between them. Whereas solids are more difficult to compress because the molecules are already close to each other. Gas molecules are very spread out. So talked about that. We said that this word definite, well, I said this, you didn't hear me because it didn't record, but another word for definite is fixed or static. So a definite shape or a fixed state shape or a static shape, meaning that the shape in a solid, the solids, they don't change shape. If you let's just look at, say, with water, and kind of makes all this easier. Water as a solid, liquid, or gas. So as a solid, you take ice from your freezer and put it onto your countertop or into a bowl, it's still the same shape. If you put it into a bowl that is a star shape, it's still going to be the same shape that it was in the freezer. It does not change shape. Now, as it turns into a liquid, it can change shape. But as a solid, it does not change shape. So it has a definite or fixed shape, and its volume is the same. A piece of ice, if you have a cup of frozen ice in the freezer, it's going to be a cup of frozen ice on the countertop. Now, again, when it changes state into a liquid, it could change. It's still going to stay the same volume, but things can change. But as a solid, it is going to stay the same shape, and it's going to stay the same volume. Now, as we add energy and a solid turns into a liquid, that's called melting. We call that melting. And so melting is the molecules are higher energy, and now this state of matter still has a definite volume. A cup of water in the fridge, in a milk jug, and a cup of water when you pour that into a bowl or onto a plate even, is still a cup of water. It does not change its volume, but it does change its shape. So looking from above, like this cylinder from above would look like a circle. Well, if you put this liquid from the circular container, like a cylinder, into a cube, or into some kind of pyramid or triangular shape, 3D shape, the water would fill all of these in, and it would be the same, it would be the shape of these things. I don't know if you can imagine that. So if you imagine putting the water in these containers as a liquid and then freezing it, it would be the shape of these things. So liquid changes the shape that it is, but it does not change the volume. The volume is the same regardless of what kind of container you put it in. All right, and then gases are kind of, they're even more indefinite. They're indefinite shape and indefinite volume, meaning they do not have the same shape and they do not have the same volume from one container to the next. So if I have a milk jug of milk and I pour that into a large bowl, the liquid is going to change its shape, but it's still going to be the same volume. Whereas with gases, if I were to release some air freshener that is in a gas form or release some methane gas into a room, it doesn't stay right there wherever I released it. It spreads throughout the entire room equally. And you can tell this when you're turning on a grill. Sometimes it's hard to light the grill because when the gas comes out of the burner, it dissipates, it spreads out very easily, and it goes into the wind, and it's not enough for it to catch on fire. If you've ever done that, then you know what I'm talking about. If not, just disregard. So those are the different states of matter. And then we get down here to the PTV sticks. This is dealing with a relationship between pressure, temperature, and volume. Pressure, temperature, and volume. And so pressure, temperature, and volume in this order, if we write it in that order, it helps us learn the relationship between them. So, for example, if in a word question, if a problem, it tells us that temperature stays the same and the amount of pressure is increasing, then do you know whether volume is going to increase or decrease? Well, if you write that PTV, a piece of paper like this, then you can be able to easily tell. So let's just say that there's some experiment done, the temperature stays the same and the pressure goes up. Well, the way that we figure out what volume is going to do is we put our finger on T, because temperature stays the same, we're going to keep it there, and then we're going to push with our other hand, we're going to push pressure up. Well, if you can imagine this, or you can even do it on your desk, when you push this P up, this V is going to go down like a seesaw. Or if you held temperature down and you pushed V up, and then P is going to go down. You can just kind of see it. You can do it with your pencil or a piece of paper. Let's say that volume were to stay the same. If volume stays the same and temperature increases, then pressure is also going to increase with it. Or if pressure stayed the same and temperature goes down, then volume will go down. And again, you can just try a little piece of pencil. If you were to try this with a piece of pencil or with your pencil and put your finger in the middle and push up on this side, then this side is going to come down. It's the same concept we're talking about. It's a little way of understanding the relationship between these two. And so that's not dealing with any real math problem. They're just understanding the relationship between these three things. And I think hopefully that'll help with some problems.